Okay, so I believe everything should be up and ready. No double audio, screen share. Cool. Okay, so the agenda for today is to continue on with the circular function stuff. Remind me, I'm pretty sure you were starting that recently, weren't you?
Yeah, I started that recently.
Yeah, okay. And how's that been going?
Oh, it's been going pretty fast so good. I just had to do some recap training. I mean, like, what do you call it?
Mhm.
Studying, because my teacher wanted us to just finish up on some, like, chapter 9 and 10 stuff. So I haven't been able to do that. But
Oh,
I was
sure.
going to do it this evening after this session.
Yeah, no, fair enough. That's no worries then. So yeah, like what I was basically getting at there is as far as like the trig stuff, we're basically looking at from 14G onwards. And
Oh,
so if there's anything pre that that needs to be refined, just let me know and I'll jump back to that. But for now, what we're
okay.
looking at is this idea of how we solve circular functions, which means you have an unknown in the angle spot and you want to figure out what that unknown could possibly be.
Okay.
Okay, so the very bare bones basics version of that is, as you see here, in example 1 on the screen share. So you have circular function equals some exact value for some specific domain. The only unknown is trapped inside the brackets of the circular function. So when you have that specific circumstance where the unknown is inside the brackets, that's when you follow these steps here. So first thing you want to make sure is the case is that you have what's referred to as an exact value expression. And that simply means you've got a circular function on one side of the equation and the exact value, or one of the unit circle exact values on the other side of that equation. That's already been done. Root 212 is one of those values, and cosine is a circular function. We've achieved what we need to do. Step 2 we'll look at in a more complicated example. And step 3 is simply just look on the unit circle and figure out where are all the spots for where cosine is equal to root 212. Now, as a reminder, when you look on your unit circle, if you're doing cosine, you care about the x coordinates. If you're doing sine, you care about the y coordinates. So if we're looking for where the x coordinates are both root 212, you can see that was going to occur at pi over 4 and at 7 pi over 4. Now, we're going to stop there because our domain is from 0 to 2 pi. If we have a different domain, we'll have a look at how to handle that. But this is about as fundamental as it gets. Just do one circle around the units, well, one revolution around the unit circle, and figure out where either the x coordinate or the y coordinate is equal to some specific value. So in this case, we just write our final answer as x equals pi over 4 and x equals 7 pi over 4. That's it for example 1. If there's any questions, raise your hand, hop off mute, or in the chat, anything like that. More than happy to go back. Next up, we look at what happens if you have to put a little bit more effort into it. In this case, we have a circular function, so we know we got to do, well, sorry, we have a circular function that has an unknown in the bracket, so we know we have to do something in this sort of framework. But the challenge that we have here is that we don't have it equaling, well, the circular function isn't on its own right now. So pretty straightforward. All we're going to do is rearrange that. That's going to get sine equals root 3 over 2. And so very similar question to before at this point now. Circular function on one side, exact value on the other. So where is sine equal to root 3 on 2? Well, that's where all the y values are equal to root 3 on 2, which is this spot here and this spot here. Therefore, we're going to hit pi over 3 and 2 pi over 3. And that's our answer. If you have a different domain, what you now have to do is figure out how far around the unit circle you have to go in the positive direction, so anti-clockwise, and how far around the unit circle you have to go in the negative direction, so in the clockwise direction. But before that, make sure you're hitting our first 2 steps, or at the very least the first step. Step 2 will be a little bit later. We have circular function on one side and exact value on the other. 0 is a spot on the unit circle as far as exact values are concerned. Now, the challenge, when you have both a positive and a negative section on your domain, means that you're going in both the anti-clockwise and the clockwise direction. So my recommendation here is to start by splitting it up into what's the positive half and what's the negative half of the domain. In this case, 0 to pi is your positive bit, and 0 to negative pi is your negative bit. You're just going to do each of those individually. So 0 to pi. If we think that if we know rather, that a full revolution around the unit circle is from 0 to 2 pi, then it means that from 0 to pi, without the coefficient of 2, must therefore be half a revolution. So we start as we always have started, and we want to figure out every spot on the unit circle where, in this case, sine is equal to 0. So the y value is equal to 0. That's going to be here and here, which means we're going to have the solutions 0 and pi for that. These are inclusive, and so we are going to absolutely include those two values. Next is, so we've done everything for the first revolution. We're now going to do the negative section, which simply means we're going to do this half circle down here. And so when you're going in the negative direction, you just need to make sure that you're either counting backwards for negatives, or you can do your flipping stuff, making sure you flip vertically to get the negative versions of those angles. Either which way you do it, you're going to have 0 again, because whether you start from, but you're still starting at the same point no matter what. And then you're going to get over here at pi, but because you're going in the opposite direction, you're now going to label it as negative pi. So in the forward direction, it was 0 pi. In the backward direction, it was 0 negative pi. And all you do is you just write all those possibilities. X is either going to be negative pi, 0, or pi, all of which would make sine equal to 0. As I said before, any questions? More than happy to field them. Because here's where it's going to get a bit more complicated. So I'll pause to see if there's anything I need to cover.
Hey Chris,
Yo.
I'll just join I think a few minutes late. Could you just show me the first two examples if that's alright?
Yeah, I'll quickly run through them. So first example was the bare bones basics. You've got circular function equals exact value, and that's what you want to achieve always, right? Circular function on one side, exact value on the other. If it's cosine, you look for where all the x values are equal to this. If it's sine, you look for all the y values are equal to this. So in this case, it's cosine, so we look for where all the x values are equal to root 2 on 2. That's going to be these two spots here, which correspond to these two angles. That's example 1. Fair enough on what's going on there?
Yeah.
Okay. Example 2, not much has changed. It just means that you don't have your exact values expression. You need to get the circular function on its own. So you add your root 3, you divide the 2, that's what these two steps are, and then it's basically the same as before. Where does sine equal root 3 over 2? That means your two y values have to be root 3 over 2, which corresponds to those.
If you you know how at the top it gave us the just a little bit up? Yeah, there it says 2 sine x equals negative root 3, f equals 0, and then you know how it says the domain?
Yep.
Let's say if you rearrange, does the domain get affected or nothing happens to it?
If you rearrange this, nothing happens to the domain. What we'll look at in question 4 is something that can change the domain, but just doing algebra as its own, as long as you have everything written in terms of the same variable, domain won't change.
Oh, good.
Yep. So we're going to answer that in a bit more detail right now with composite functions. So basically, we've got a whole bunch of nastiness inside the circular function now. Not the end of the world. You don't necessarily have to do what I'm suggesting here, but I've found that this is probably the easiest way to get introduced into circular functions, which is to just sort of take this big mess of numbers and letters and just try to make it look more like what you've already seen before. So again, first things first, you want to get the circular function on one side and an exact value on the other. That's pretty chill. Just add a half to both sides. There's the circular function. Even though it is complicated on the inside, it is still the circular function on its own, and the exact value on the other. Now, because it's not just x on the inside here, makes it look complicated. So my personal recommendation is to take whatever's on the inside of these brackets and just replace it with a single letter. So we're going to say u, some other letter, is equal to 2 bracket x plus pi over 4. That's what this is all about. Now, the problem is when you rewrite your function now, so you replace the brackets with u, that's cool because now it looks like pretty chill. But what happens is that now you've got this x domain, but this u variable to work with. They don't really work that way. And so one of the things you'll have to do if you want is update your domain. And when I say if you want, there is just a continuous guess and check that you could do. But if you want to know for certain how many solutions there are without just repeatedly guessing and checking, then what you do is you take your x domain and you sub it into your u equation, which means you take each of the individual x values and you plug it into the x spot on that u equation. So if I take this x equals 0, if I put it in there, that's what this bit looks like. And so when you simplify that, that means that the new lower bound is going to be pi over 2 after you simplify all of this. That's converted this x value of 0 into a u value of pi over 2. We do the exact same thing for the upper bound. 2 pi goes into that spot. Right, 2 pi goes into that spot. Simplify, simplify. This is our new upper bound. And so we've gone from having this, which is a bit of a complicated mess, to now having this, which this looks a lot nicer to work with. This is not great, but you'll have to get used to doing these regardless. A lot of domains, even in X, are usually not going to be quite as simple. It's just 0 to 2 pi. So doing this will kind of happen regardless. So this is my recommendation for how you can simplify things. From there, you just solve it as if this was your starting point now. If this is where you started, it would just be like, okay, cool. Where does cosine equal a half? Well, that's where the x coordinates equal a half, which starts at the angles of pi over 3 and 5 pi over 3 if we just considered one forward revolution. But in this case, we have a little bit more than a forward revolution. We actually go all the way up until 9 pi on 2, which if you convert that to like a whole and a decimal, right, we're thinking about like roughly 4.5 pi. So if 2 pi is one revolution, 4 pi is a second revolution, and then 0.5 is another half on top of that. So you're going twice and a half around the unit circle. Wait, sorry, is it twice and a half? No, twice and a quarter. Yeah, because it's 2 pi for a full revolution. Point being, you can do that quick conversion to figure out where your upper bound is, how many times you want to go around. And so we're going to do exactly that. Now, you don't have to manually count around a whole bunch of times. What you do is you take these two values that you just found that you can easily look at or have memorized, because you'll need to have this memorized, and you just add 2 pi to those. That's the same thing as doing a revolution starting from that spot. And the reason why is, well, once again, 2 pi is a full revolution. So if you start at pi over 3 and add 2 pi, mathematically speaking, or maybe even visually speaking, that's the same thing as saying start here and do a full revolution. Obviously, you're going to get back to where you started, which is why you hit that same spot. We're just going to keep doing that until we exceed the domain. And we exceed the domain at 17 pi on 3 in this case. So it can be a bit difficult when you have a different denominator in your solutions compared to your domain. This one's a divide by 2, this one's a divide by 3. So if it's at all challenging to figure out which of these is bigger, just put them into the same denominator. Do a little cross multiply. Multiply this entire side by 3, this entire side by 2. That'll get it into the same denominator of 6. But yeah, once you've got your full list, just write it all out and make sure that you chop off anything that's either too big or too small to fit in the domain. We want to be between pi over 2 and 9 pi over 2. Pi over 3 is a little bit too small for that. It's just a little bit before pi over 2, so we cut that one off. And 17 pi over 3, as we just said, too big. So that simplifies down to simply just going to be that. And And that gets us the solutions. That's how we would normally stop if that was our starting point. Unfortunately, it wasn't our starting point. We have solutions written in terms of u, but our original equation was in terms of x. So all we're going to do from there is make sure that we get our solutions back in terms of x. These u values, we already know that u is the same thing as 2 bracket x plus pi over 4. So every single u that we've written down is now going to be replaced with this. That's going to convert us from u back into x. And so in this case, instead of saying u equals all these things, we now say 2x plus pi over 4 equals all those things. Last up, rearrange for x. So in this case, that means divide everything by 2. That'll cancel this one out and make all these a denominator of 6. That's usually the easy bit, just changing all these to a 6. What's a bit more challenging is if they choose a difficult subtraction, like I've done here, then it means that you're going to have to change your denominators again to make that subtraction appropriate. Normally they're not too nasty with this. They'll pretty much always choose the addition or subtraction to be the same denominator that you end up with. That way you don't have to spend that much time on the question. But that's more so for like exams. The book will throw all sorts of nonsense at you. But as like an exam tip, what's going on there is they have to pace it so that it's roughly 1.5 minutes per mark, 90 seconds per mark. And so if they give you a nasty question like this, they have to give it a lot of marks. And the assessors aren't necessarily incentivized to give a lot of marks for the same topic. They want to do a whole lot of things, which is why you usually won't see this on like an exam. This is probably what they'll start testing in SACs or definitely in the books at the very least. That's just to set some expectations around what you'll see, at least this level of complexity. But yeah, that's going to get everything back in terms of x. And if you compare that back to our original domain of 0 to 2 pi, you'll see that everything fits in there, and there's no spillover. You can see this one was really close to it too. 23 pi over 12, that's almost 24 pi over 12, which is almost 2 pi.
Chris?
Yo, what's up?
You know how it says first divide everything by 2?
Yep.
Would you just show me like one example, like exam? I think I'm like messing up a little bit.
Oh yeah, so all
Like,
these divide by
yeah,
2.
so like just one example, if you could just show me like in the written bit,
Yeah,
just
so
how to like divide it by 2, because I think I'm getting it confused how to like do that.
yeah, okay. So dividing fractions, what I'll do is I'll do it in like a very fundamental, like fundamentals of fractions way. So let's say we have the 5 pi over 3, 5 pi over 3, and you want to divide that by 2. So whenever you have whole number and fraction, basically the easiest way to go about this is to literally just rewrite this as a fraction. Right, that way you've got 2 fractions to work with and the rules become slightly clearer on how you handle it. Then from there, when you have a division like this, do you remember what happens to this right hand side?
Yeah, so reciprocal.
Yeah.
Yeah, I was just getting a little confused, yeah.
Yeah, okay. So you can see now you're going to have 5 pi over 3 times 1
Yeah,
over
yeah.
2, and then that's going to be 5 pi over 6.
Yeah.
Fair enough?
Yeah.
Sweet. Okay, so that's why all these are now going to have denominator 6. And then everything else, yeah. Anything else to cover for this one? I'll take a pause, see if anyone wants to ask a question, because this is probably the most complicated it'll get. All the other examples are a bit more niche, but I think they're almost a bit easier as well. Okay, and if there's anything, just pop in chat or hand up, anything like that. Alright, we can also use null factor law. It isn't just for polynomials. Null factor law simply states that if I have 2 things that multiply together and the result is 0, so if I have this multiplied by this equals 0, then either the first thing or the second thing must have equaled 0. There's no other way to achieve that. Well, or both, I guess. But we didn't start with this, we started with this. And so the way that you can figure out that null factor law is applicable is first, can I get my equation to equal 0? That's usually doable, right? I don't think there's any circumstance where you couldn't get your equation to equal 0. But the point is, when I have got it to equal 0, is there any factorization I can do? That's why you need to be a little bit careful with your with the notation, right? You need to be aware that cos squared x, written like this, is the same thing as saying cos x squared. All right, so you need to know that this is just cos x times cos x. Just a bit of a notation thing. And so if you got cos x, and then another cos x, well, there's a common factor of cos x. That can come out the front. Then, as I said before, either this or this equals 0, and so now you're just solving two sets of circular function equations individually, and then combine the results at the end. So this one's going to be your cos x equals 0, this one's going to be your cos x plus 1 equals 0. So we'll start with this one. For cos x equals 0, where are my x coordinates equal to 0? That's going to be that and that, which of course is going to refer to pi over 2 and 3 pi over 2. We have a domain of 0 to 2 pi, so we're only going to do that forward revolution. And then for cos x plus 1 equals 0, well, first thing we've got to do is knock the 1 over to the other side, and then that's going to allow us to quickly look from a full revolution, where does the x value equal -1? And that's that spot. So in total, you're just going to combine the two answers. Just separated by commas, nothing crazy. You can maybe even do like x as an element of all of these, and you can use set notation. That would be like the most mathematically sound way possible. So if you are shooting for really, really good marks, then that'll be seen as a more favorable, or it'll be seen on more favorably as a solution. I'll just write that out just so we can get a visual of that. So if you want to be super mathematically sound, you might say x is an element of squiggle brackets pi over 2 comma pi comma 3 pi over 2 squiggle bracket. That's if you want. Otherwise, what I've got written in the book is fine as well. Next up, you can also convert to tan as a solution. The thing to identify here, if you have cosine and sine in the same equation, very likely that converting to tan will be possible as a solution. And so the way that works is at some point in your simplification, you're going to divide both sides by the cosine. I should probably point out a bit of a nuance there. They have to have the same thing in their brackets. Otherwise, it's not going to work. You can't just have sine and cos. You have to have the same brackets as well. But the reason why dividing by cosine is important is because sine divided by cos is tan. By definition, that's what the ratio is. And so, sure, we do a bit of rearranging first, but if I divide both sides by cosine, I get sine over cos, which is tan, and I get cos over cos, which is just 1. Or in this case, -1, because it's multiplied by the negative on the outside. And so what used to be a complicated thing of two separate circular functions is now just one circular function that I can rearrange, get it on its own, and then solve like we're already used to. In this case, it's using tan, so a little bit tougher than sine or cos because it's less common, but still the same thing. Where does tan equal -1 over root 3? That's going to be here and here. So if you've memorized your tan values, then you'll be able to do that just off rip. If you prefer the sine and cos variant, then you just want to figure out what y divided by x will give me -1 over root 3, which is a half divided by -root 3 over 2, or the other way around, where you have the negative on the half instead. That's if you want to do the math way, which don't necessarily recommend, but it's there for people because, well, it's an option. And then, yeah, we just got a bit of a rearrange at the end because, well, we had 2x in the brackets. We didn't have just x. So we had to do that whole substitution thing from earlier, where you replace the inside of the brackets with a u, and you fix up your domain accordingly. We were 0 to 2 pi, so if it's 2x, we're basically doubling each of these values. 0 doubles to 0, 2 pi doubles to 4 pi. That gives us our full list. You put the 2x back in, divide everything by 2. Now everything's back in terms of x. That is solving circular functions. So those are basically everything I've come across when it comes to solving circular functions. The last two examples were unique to Saxon exams. Everything else you'll see in the book. Yeah, and I got plenty of Sax on this. So I think every functions and relations Sac has at least one of these methods in it. So you'll be able to practice them there. Any questions before I move on? I'll give it like 10 seconds or so. A weird hyperlink. A dash immediately after it. Anyway, that's what I got. So next up is the general solution to a circular function. So basically all we're going to do is slightly change what was going on in the previous framework that we were following. Literally, well, I guess I'll say, you'll notice that pretty much everything in here is the exact same wording, right? Like we're doing our rearrange, we're doing our substitute, we're finding solutions, we're getting it back in terms of x. All we're doing is sliding in this plus 2 pi n into each of our set of solutions. And the reason why is because what a general solution does is it tells you all the possible solutions to the circular function. So none of these questions are going to have a domain associated with them. It'll just say solve circular function equals value for all x, or just for x. If there's no domain, that's your clue that you have to give a general solution to it. Usually you don't have to read into it that much. It'll usually just say find a general solution for it, and then that will be all you need to worry about. But yeah. And the reason why we need this is because, well, circular functions could repeat forever, right? If you remember the graphs of circular functions, they repeat every 2 pi, or at least every period, and that can go on forever unless you restrict your domain. And so what we're doing here is making sure that we have some sort of formula that can tell us what the solution is going to be, no matter how far in the forward or negative direction that it goes. That's why we have it. As far as what you actually do, really nothing's changing all that much. So, where does sine equal negative root 3 over 2? Well, that's these two spots. That's your first step, always. Figure out the 2, sometimes 1 spot on the unit circle where your exact value is located. That's going to be the 4 pi over 3 and the 5 pi over 3. At this stage, you add your 2 pi n. So you take your 4 pi over 3 and your 5 pi over 3, you slap 2 pi n on the end, and if you want to be super specific and mathematically correct, you'll say that n is an element of the integers set, because n is going to basically kind of stand for the number of revolutions you're going around the unit circle with. It only kind of does, because n equals 0 is the first revolution, and n equals 1 would be the first positive. And n equals negative 1 would be the first negative. So it's a bit offset a little bit, but you can more or less think about it as just how many forward or backwards revolutions are you doing. Yeah. N being positive means you're going in the forward direction, n being negative means you're going in the backwards direction. That's it. That's the entire thing. When you have your solutions, slap 2 pi n on it at the end, and that's all you really need to know.
Chris?
Yep.
So every time we don't have a domain, we have to put on the 2 pi n.
Well, it depends on how the question is worded, of course, but if it's worded like this, just solve the circular function for x, If there's no domain associated with it, then yeah, you give the general solution. If it's like an application question though, and there's a clear domain that isn't necessarily explicit, like for instance tidal waves over 24 hours, they might not have said 0 to 24, but the implied domain is 0 to 24. So I guess all I'm trying to say is, like, don't think that just because you don't have exactly this written, that there isn't some implied domain. If there's no implied domain, then yeah, you're doing this. But if there is, you're doing the previous stuff. Cool?
Just a question.
Yeah.
Why can't we leave it as x equals 4 pi on 3 or x equals 5 pi on 3?
Because that's not because you haven't solved every possible solution to it. Because
Okay, so we need to solve for every possible solution of x.
yeah, solve it for
Okay,
x.
okay.
Like if you put it in the CAS, this is what the CAS will do if you don't put a domain on the solution. Yeah. So I guess maybe one way to think about it is that if there's no domain that's said or written or even implied, you assume all real numbers for your domain. That's maybe another way to think about it. But okay, that's sine. I do have another few examples for cosine and tan, not because they're all that different, but because there is a way to further simplify what's going on in the general solution. And this is for people who want to get like a slightly more favorable looking answer. If you don't, then don't worry about what I'm about to say, but this is if you want to tidy it up a little bit more. So cosine equals negative root 3 over 2. Rearrange if you need to, substitute if you need to. We're just looking at fundamentals here. Where does cosine equal negative root 3 over 2? Well, that's these two x coordinates, which means it's these two angles. And so if you're following my guide, it pretty much just means you slap 2 pi n onto both of those and you call it a day. However, in the case of cosine, there is a further simplification. And the reason why is because the solutions to cosine will always be vertically flipped from each other. So if you have 5 pi over 6, you're also going to have 7 pi over 6. If you have pi over 3, you're also going to have 5 pi over 3. That will always be the case for the cosine general solution. And for that reason, because they're vertically opposite each other, it simply means that you can ignore one of these solutions and just write a plus minus on it. Because this spot here is the same thing as negative 5 pi over 6. And so that means instead of writing two separate solutions, I can now, well, first maybe rewrite it into a positive and negative version of that. But then I can condense that down even further and just say plus minus at the front. That's just a further simplification should you wish to do it. It also means less writing as well, so that's the other advantage. But yeah, not required. You can just follow those steps and ignore this. Tan's simplification. So once you get your two values for tan, you're going to have that 2 pi n term on both of them. That's perfectly fine. Alternatively, what you can realize is that wherever your tan solutions are, they're always going to be exactly separated by pi every single time. If you have here, you have here. If you have here, you have here. All right, they're always going to be one semicircle away from each other. And so what that means is, instead of putting 2 pi n, which means a full revolution, you can now put pi n, which is that half revolution. And furthermore, because you're doing half revolutions now, you don't really need this second spot anymore, because you can now just say pi over 3, half revolution, half, half, half. You don't need this second spot in your equation anymore. And so usually we knock off the bigger one, leave the smaller one, and then just put a pi n there instead. That's the simplification there. Lastly, this will be important to watch out for, which is when you have anything other than just x inside it. The reason this is important is because the order in which you do things is going to matter a lot. Everyone gets this wrong on the first try. This is my attempt at trying to avoid that. So, do all the steps as normal. All right, rearrange if you need to, substitute if you need to. In this case, we do, or at least we could if you wanted to. Replace the 3x with a u. The good news is there's no domain that you have to consider. So really all you got to do is just sort of chuck a u in there. Now, from there, solve this. What are the two spots for where sine equals negative root 3 over 2? Well, that's these two spots here. It's at this specific stage where you add 2 pi n. You add 2 pi n at this stage. Then you rewrite for x. So you have your 3x's back in there, and when you divide by 3 on both sides, this also gets divided by 3. Everyone forgets this bit. Don't forget it. That's really all. That's the only thing you have to worry about. Making sure that when you do your rearrangements for x, it also impacts the 2 pi n term. It is, in fact, still in the equation. Otherwise, that's it for general solutions. There's really only one thing you have to watch out for, maybe two, if you want to consider the fact that the order in which you do things is going to matter. Depends on how you look at it. Any questions on those? Does anyone have a preference on where we start? Whether we do like the previous document or this document's questions? Because normally, last few times I've done this lesson, we start at the solving circular functions. Curious if anyone wants to get like some practice into the general solutions first. Okay. We'll do at least a few basics just to make sure we got those down, and then we'll spend some time on the general solutions. Okay, so what I'll do is I'll get a screenshot of the summary that we follow, so you can refer to that. Should probably also get a unit circle up as well. That'd be a good idea for you. And unit circle, should you need it. And sine and cos. Okay, cool. So we'll do one of them live, just so we can all be on the same page, at least for the first one. So cosine equals 1/2, and we're doing it between 0 and 4 pi. So before we go to the actual handwriting, I'll first identify why it is the way we're going to solve this. So you're finding all the x values over a certain domain with pi in it. So already that should be one tell that would tell you that you're solving using the method that we've just discussed. The other tell is that the x is inside the brackets of the circular function. And I say brackets with air quotes because they didn't actually put any brackets in it in this case, but that's the intention. Those two things combined tells you that we're trying to solve for cosine equals 1/2, and we're doing it from 0 to 4 pi. So I'll just write that down. Cosine x equals 1/2, 0 to 4 pi. I guess you have to assume that it's square brackets between 0 and 4 pi. I mean, that wording would almost actually imply rounded brackets between. I just think it's a bit loosely worded. I don't think the book intended one way or the other. It's not actually going to matter for the solution. But anyway, so based on the results I've provided you as screenshots, what do you think we should do first?
Would we just find all the x values which equal 1/2?
The x values which equal 1/2 is correct. Yeah, precisely. Cosine being the x, of course. So you're going on your unit circle and you're looking for where all the x coordinates on the unit circle is equal to 1/2. So once someone has those, let me know what they are.
So it's pi on 3,
Yep, that's one of them.
2. So would it only be positive?
Yeah,
Positive 1 over 2?
only positive. Yeah, that's correct.
Okay.
You want to make
And
sure that
5
this.
pi on 3.
Yep. Cool. Those are the first two solutions because that will cover one forward revolution. This is where we're going to be careful of the domain though. So we're doing 0 to 4 pi. How many revolutions does that mean we have to do?
2.
2, correct. So we don't necessarily need to count again from here. What could we do to quickly figure out the other two solutions?
We could just add 2 pi.
Just add 2 pi. That's it. Yeah. So if you don't want to count, which, I mean, this one wouldn't be the end of the world to continue counting in terms of pi over 3s. But yeah. So you'll have pi over 3 plus 2 pi, and then 5 pi over 3 plus 2 pi. 2 pi is the same thing as going to be 6 pi over 3, so you're looking at 7 pi over 3, and then you're looking at 11 pi over 3. Just so we can all be on the same page, I'll pull up the screen share. So on the screen share, the pi over 3 and the 5 pi over 3 spots are here. And you'll notice that on both of those, the x coordinate is a half. Right, that's what we're looking for. And we're going to, of course, go the second revolution to make sure that we've hit 0 to 4 pi. Any questions there? Sweet. Okay, that's a fundamental. So, do they have anything else? Yeah, we could probably squeeze in a... Yeah, we'll do a question 5. So going from negative pi to pi. So I'll get down, let's call it sine x equals root 3 on 2. And we're going from negative pi to pi this time. Same deal. I'll get some thoughts as to how we might start this one. Actually, I'm going to modify it just a little bit, just so we can actually make use of that negative domain. We'll make that a negative 2 pi instead of a pi.
Or do we find all the y values that are root 3 on 2?
All the y values that are root 3 on 2. Yeah, precisely.
So that would be pi on 3 and 2 pi on 3.
Yep, pi on 3 and 2 pi on 3 are good. X equals pi on 3, 2 pi on 3. What else do we have to do to continue?
Do you need to figure out how many revolutions you have to add?
Correct. Yeah, so what we've just done now, how far around the unit circle have we gone?
I think just under a half.
Yeah, just under a half, correct. And so if that upper bound is pi, do we have to go any more forward?
No.
Correct, yeah. So if I divert your attention to the screen share unit circle so we can all see the same circle, we've just hit these two spots here, right? We've hit the y value of root 3 over 2 here and here. The next time it's going to be positive root 3 over 2 is all the way back here, right? So we can't cross this barrier, which means we've done our forward revolution. Cool. But we do have a negative 2 pi that's going on. How can we handle that part?
Would we just subtract 2 pi?
Yeah, just subtract 2 pi from everything. Precisely. So, pi over 3 minus I'll rewrite it as a fraction, so 6 pi over 3, a bit easier to see. And then 2 pi over 3 minus 6 pi over 3, with a reminder that 6 pi over 3 is the same thing as 2 pi. So 1 minus 6, so minus 5 pi on 3, and then we're going to have minus, what's that, 6 by 4, minus 4 pi on 3. Okay, that's cool. So we got these two as solutions. We got these two as solutions. Do we need anything else? Have we gone far enough in the negative direction?
Yep.
Yeah, correct. We have. Because if you look at the screen share again, negative 5 pi over 3 and negative 4 pi over 3 are the exact same spots that we just talked about earlier, but those are the negative representations of them. And so once again, to get back here from a negative direction, you have to cross this negative 2 pi barrier before you hit those spots, and for that reason, we're sorted. Yeah, that's it really. Cool. If there's any questions, feel free to let me know. Otherwise, this might be a good opportunity to have a look at the general solution.
How would we write that as a solution?
Yep. So I have pretty much always gone down to just saying x equals pi over 3, comma, 2 pi over 3, comma, minus 5 pi over 3, comma, minus 4 pi over 3, and just leaving it at that. Perfectly fine. If you want to be mathematically super sound, you replace this equal sign with an element, and you'll put them in squiggle brackets. That'll be the most mathematically sound way you can do that. It doesn't really matter if you put negatives last, positives first, in whatever order. These squiggle brackets simply mean that everything separated by commas exists in X. So it doesn't imply that it has to be in a particular order. That's pretty much it there. If you want to make it look cool, you might put your negatives first and your positives afterwards, just to be conventional, but it's not wrong per se. Okay, general solutions. So I'll grab a screen grab of the framework for that one, and we'll spend some time here. Okay, that's that. Yeah, let's chuck a tan in there. Why not? You have a tan unit circle, same thing. Okay, we got root 3, we got tan, and we've got, yeah, root 3 tan x equals negative 3. This will probably be a bit of a test. So remember, we're doing general solution here. There's not going to be a domain associated. Have a think about it. What could we do to start this one off?
We have to find all angles which equal negative 3 on root 3.
Yeah, that would be correct, yeah. So the first implied step in there is divide everything by root 3, and the reason why is because you want to get the circular function on its own, and an exact value on the other side. Now you are going to run into a bit of an issue if you can't remember a specific technique, the issue being that it appears that this isn't going to be on the unit circle. It appears that way anyway.
Would it be that we have to look at the sine and cos circle, and we have to find we have to look at the x and y and see which ones divide to that value?
You absolutely could do that. Yeah. So if that's your preferred approach for doing tan stuff, then yeah, you could figure out a way of achieving that, which, well, I don't think that might not work actually, because you've got negative a half, divide by that. Oh, sorry, it's the other way around. Yeah, y divided by x. You're going to get negative 1 on root 3. Yeah. You're not going to get an exact match there, at least not the way I'm looking at it. There is another method you could approach, which is, you could use, which is rationalizing the denominator. And so what that simply means is you're going to multiply the top and bottom of your fraction by the root term. So you take your negative 3 on root 3, and you multiply the top and bottom of that by root 3. You'll get to a stage where the root 3's will become 3. You'll have a negative 3 root 3, because that'll condense down into itself. And then you'll see you got a common factor of 3 that you can cancel, which means that this is actually the same thing as just negative root 3, which, now that I'm thinking about it, probably meant that I was looking at the wrong thing. No, even then, the half and the root 3 over 2 weren't going to get you to equal negative 3 on root 3. Yeah, I mean, it was a good idea, right? That'll be super useful for if it's written conventionally, which is where you have your root 3, 1, and root 3 on 3, when it's got those rationalized denominators. In other circumstances, a bit harder to work with, which is why I don't usually recommend doing the sine and cos thing. Anyway, all that to say is just we want to figure out where does tan equal negative root 3. That's the take-home message there. I'll pull up the unit circle as well so we can all look at the same thing.
So would it just be 2 pi on 3 and 5 pi on 3?
That's it. Yeah. 2 pi on 3, 5 pi on 3. Awesome. Almost done. What do we have to do that's a little bit different for general solution?
Plus 2 pi n?
Plus 2 pi n. Yeah. So on each of these individually, I'm going to do 2 pi on 3 plus 2 pi n, and comma 5 pi on 3 plus 2 pi n. If you want to be a bit more cooler with the answer, you'll say n is an element of z, and you'll probably just do a z with a... It's not super like what it's meant to be with the double stroked diagonally, but I can't double stroke diagonally, so I'm just gonna... They'll know what you mean. Now, that is a valid answer. Gets you 4 marks. Anyone know how we can tidy this up? There's a way to get it down to just one statement instead of 2 statements.
Would we just do like plus or minus 2 pi on 3 plus 2 pi n?
Plus minus 2 pi over 3 plus 2 pi n. You're thinking about the cosine one, which it's good that you've picked one up. Plus minus 2 pi over 3 would be these 2 spots on the screen share.
Oh, okay.
So the thing with tan is that they're separated by pi, right? So these are always separated by a semicircle away from each other. And the tan specific one, which obviously you don't need to have, this is just for extension, you pretty much just chop off the second solution there, and you chop that off there. You're now saying 2 pi on 3 plus pi n, because if you have n equals 1, that's the same thing as saying 2 pi on 3 plus pi, which actually is 5 pi over 3. You include that in one separate solution. That's all. Not required, just for fun. Okay, I'll grab one more example. This should take us to the end, if not a little bit over. Cool. So this will be where we have to handle the composite function scenario. 2 cosine 3x is equal to root 3. Okay, what shall we do?
We would make 3x u.
Yep. 3x equals u. Oh, that's not a u. Let's try that again. 2 cos u equals root 3. That's cool.
And we would make it cos of u equals root 3 on 2.
Yep. Dividing both sides by 2. Nice. What else?
Then we would find all x values which are root 3 on 2.
That's it. That's good.
So which would be pi on 6 and 11 pi on 6.
Pi on 6 and 11 pi on 6, correct. That's those two there. So we've got specifically u equals pi on 6, comma 11 pi on 6. Yep.
And then you just do 3x equals 2 pi on 6 and the same for 11 pi on 6.
3x equals 3x equals pi on 6, comma 11 pi on 6, like that.
Yeah.
Okay. What else?
And then we would just divide it, which would give us pi on 18.
Yep.
And yeah, 11 pi on 18, yeah.
Okay. Are we done?
Is it a general solution or?
It is supposed to be a general solution. Yep.
So would we add the 2 pi in?
We do add the 2 pi in, yeah. But at this stage, it's too late. Where do we have to add it?
Before we divide it by 3?
Correct. Yeah, before we divide by 3. Nice. So basically just going to come in here and put in our plus 2 pi n, and then it was 11 pi on 6 plus 2 pi n. And the reason why is because you want to actually divide this 2 pi n term as well, if there's any divisions. X is equal to pi on 18 plus 2 pi n on 3, and then the same thing over here. Now, some solutions in the book will put all of this over the same denominator. That's nothing crazy. Just multiply this by, what, 6? Yeah, multiply top and bottom by 6 here, and you get them the same denominator. So that's what you might see in an actual, in the book answers. They'll put it over the same denominator, and they might even factorize the pi out as well. Just warning. So that will look like, so we got x equals pi plus 12 pi n all over 18, and then I'll take this pi out the front for whatever reason. 1 plus 12n, and it looks kind of weird, but that's what they're known to do. There's that, and there's also, if you want to go for extension, it means you can chop this off, and we can do that plus minus that we were talking about earlier, because with cosine they are vertically opposed from each other. So you can just grab this here, put your plus minus. This is where it gets weird, because now the plus minus has to be on the 1. So this factorizing stuff looks even weirder. What they end up doing is they go plus minus on that, and they put the pi here, and it just looks like nonsense. But you might see it, so there it is. That's about it from me. So, if there's anything you want me to clarify further, I'll stick around for a little bit. Otherwise, have a good night.